Thank you, first of all, for the invitation and to all of the organizers. It's a pleasure to be here, and particularly that this happens in presence. So today I'm talking about a joint work with Marie-Claude Arnaud, who is in the audience, and Jessica Massetti from University of Roma Tre. So we'll try to give some motivations on this talk. So mainly I want to discuss the persistence or the existence, if you want, of periodic Lagrangian tori for family of twist maps of the annulus. So let me just start by giving some motivation of that led us to this kind of investigation. So there are several questions in dynamical systems in which one wants, for example, to classify integrable maps. For example, two main examples are in billiard dynamics. One wants to understand what kind of billiards are integrable. This is the so-called Birkhoff conjecture. Or there are also examples in Riemannian geometry, for example, Riemannian matrix on a torus, trying to understand which one are integrable. And so in trying to understand this kind of questions, so one possible way is to study what happens locally. So if I'm close to an integrable map or an integrable flow, and I know that the perturbation remains integrable, what can I say about the perturbation? And so this was, for example, used in a series of work with Vadim Kaloshin and also other collaborators to tackle a local version of the Birkhoff conjecture. And so the main idea is that when I have an integrable system, it has several features, and some of them are very robust, so they persist under perturbation. So for example, for those of you that know KM theory, I know that if I perturb an integrable system, then many invariant tori will still persist. But then some other features are more fragile. And then if I know that a perturbation leaves invariant these features, then maybe this translates into some special property of the perturbation. And so if I have several of these features persistent, then maybe this gives a sufficient number of conditions on the perturbation to say something more explicitly about the perturbation. So this is just a general idea. Now, what we want to do, we wanted to understand this question in a sort of more general setting than just billiards or some specific examples. And so we started by studying twist maps of the 2D dimensional annulus or 2D dimensional cylinder. So let me just specify what is the setting. So if you cannot read, I write bigger, larger, let me know. So the first definition is what do we mean by a twist map of the 2D dimensional annulus? So we have a map from TD cross RT to itself, then it's a C1 diffeomorphism. And we assume something on this map, namely actually we put some assumption on the lift of this map, so such that it admits a lift from RT to RT to itself that satisfies the following condition. So let me call QP the variable of this map and capital Q, capital P the image of this point. So then the conditions we ask are the following. So the first condition is that for every M in ZD, if I look at FQ plus MP, this is just FQP plus M0 for every QP. Then the second condition is the so-called twist condition that was mentioned in the talk by Marie-Claude also yesterday. So it can be expressed in the following way. If I look at the map that to QP associate Q and consequent the image point Q, this is a C1 diffeomorphism. And then the third condition is we want this map to be symplectic, so it preserves the symplectic form, and actually exact symplectic. So so this is exact symplecticity. So this can be expressed in several ways. One way is to say that it exists a periodic generating function. So namely that there exists a function S CQ such that so S is periodic. So S will depend from Q and capital Q. So actually the twist condition is saying that I can use Q and capital Q as new coordinates if I want. And so periodicity is that if I make a integer translation of this map, this is the same. And then the second condition is that if I look at P the Q, where actually this P is a function of small q and capital Q, so I compose with the inverse of this map, minus small p dq, this is the same as the differential of S. Okay, so the second condition implies that is a symplectic, so it preserves the symplectic form, and actually the fact that this function S is periodic, so it means that if I look at the map on the torus, on the cylinder, then actually is exact. Okay, so these are the conditions we ask. Actually, one can ask less stringent condition. For example, can just consider a finite annulus or instead of the cylinder, but just for the sake of this talk, let's consider these. And also the twist condition can be expressed in different ways, but for the sake of this talk, let me assume this. So let me do an example that is a trivial example, so a completely integrable map. So what is a completely integrable map? Will be a map of the form. So I write directly the lift. FQP is the same as Q plus gradient of LP P, where L is a CQ function on R. And then I ask that the gradient of, sorry, of RT. The gradient is a C1 differential. Okay, so if I have such a map, then actually the dynamics is trivial to describe in the sense that, so let me look at this map. So this is D and these are D, so actually the projection. So what I'm saying is that if I spin out, then if I look at the torus where P naught is constant, then this is left because P is essentially a collection of integral of the maps. And then the dynamics here is just a rotation where the rotation vector is given by this number. Okay, and so everybody here well knows that the dynamics here depends exactly on the arithmetic properties of this integer, this vector. So if, for example, the dynamics can be an orbit winding densely on the torus, or actually it can be decomposed in subtori of lower dimensional subtori. And so let's say in the most degenerate case, it can decompose into foliation by periodic orbits. Okay, so essentially, according to the arithmetic properties of these vectors, these tori are somehow more robust or less robust. So if I do a perturbation of the system, AM theory says is there's some assumption on the map, then tori corresponding to orbits that dance windly on the torus, and actually that are very badly approximated by rational, then they will survive, and so they're more difficult to destroy. On the other hand, if I have a torus made by periodic orbits, then that's very fragile in the sense I expect that whenever I make a perturbation, this degenerate foliation by periodic orbits. And so the idea that we want to analyze is exactly this. So we want to understand what can we say about the persistence of this tori, so tori foliated by periodic orbits, for some families of twist map. Okay, so if I put that the twist map remains integral, this tori should persist. And so we want to understand what kind of implication, information on the kind of perturbation this condition gives. Okay, so let me introduce the main object. So keep in mind this example that we will get back to this. Actually, the generating function in this case, I just write it that I will probably use it later. It's nothing else than H Q minus Q, where H is the Fenchen-Legendre dual of the, well, under some assumption of L. So H of S is the sup of over P of PS. Okay. Okay, so let me define what is the object in the title. So what we mean by periodic torus. So let me say periodic graph. Oh, let's say periodic torus. So there is always this question that I will move continuously between this and the lift. So here is a torus, here is just a periodic graph. Okay, so let M and N be a couple of ZD, and this is M is an integer, an integer vector, and then is a natural number, not zero, and assume that they are co-prime. So I apologize that M and N look very similar to each other. So we say that, and then let gamma from RD to R, Lipschitz, well, at least Lipschitz, and ZD periodic. Okay, so the lift of a graph on the torus. And so we say that, and so we consider the graph of gamma. So we say that gamma is Mn periodic. Torus. If I look at the nth iteration of the map and apply it to any point on the graph, this just goes to the point translated by the integer vector M and gamma of Q. Okay, so what I'm saying is that these points are left invariant. Well, the projection of this point in TD cross RD is invariant. Point gets back to the original point after an iteration. Just a small remark: I'm not asking that actually every iteration of the map remains of the graph. So in principle, what could happen is that if this is the graph, then I know that the nth iteration of the map goes here, but then it could happen in principle that the other iterations are not on the torus. Okay, we will see that is not the case actually under some assumption. And let me just, to be more precise, we say that the torus is completely periodic. If it is also periodic, it is also invariant. Okay, so every iteration of the map on the torus. Okay, and so just a remark. So if I have some assumptions on the map, on the twist condition of the map, I will be more precise in a second. And actually, one can show that being periodic and Lagrangian implies being completely periodic. So actually, it's not really a generalization to ask the torus just to be invariant by the nth iteration of the map. So Mn periodic plus Lagrangian implies completely periodic, but implies invariant. Okay, plus the map F is positive. I will explain in a second what is the degeneracy condition on the map. Okay, and so the proof of this, I will not do it, but it's easy in the sense what one can show for people that are familiar with action minimizing methods is that if you have an orbit that satisfies this M periodicity condition, then it must be, so that is on this graph, it must be action minimizing. And then actually the fact that it's invariant follows from the uniqueness of action minimizing Mn periodic orbits after if I fix the starting point. Okay. Okay. Sorry. Yes. Yes. Yeah. So thank you. Okay. So so to state the main theorem, let me put some extra condition on the map. Namely, I want to define some non-degeneracy condition on the map. So what I want to do, I want to make this twist condition slightly more precise. And so definition. We say that F is positive if there exists a so S here is called the generating function. such that if I look at the mixed derivative of S with respect to small q and capital Q. So this is so negative definite as a quadratic form. Okay, so this is less or equal. So there exists alpha bigger than 0, such that it's less or equal than minus alpha norm of d square for every Q and capital Q. Q and capital Q in RT and D in RT. Okay, so one could wonder why it's positive since it's negative, in the sense that the map is positive. But remember that because of this condition, what you can see is that if I take the derivative of Q, capital Q to respect small p, this is the inverse of minus the inverse of this. Unless I mixed up, so this small q. Okay. So essentially, the negative definite of this map is related to the positive definite of this condition. Okay, and then we say that f is strictly positive, not strongly positive. If also the other, I also have a lower bound here. So if it is positive, and there exists also beta, such that the other inclusion holds. Okay, so it's easy to construct examples of these maps. So essentially, this is nothing else than a quantitative version of the twist condition because of this property here. So if you go back to the integrable example, this condition here translates into conditions. So in the completely integrable case, so this condition translates into looking at the Hessian of this function L. And then being positive means that this is positive as a quadratic form, and being strongly positive, that is also as a bound from above. It's positive. Strongly positive, I don't write it. I also have the other condition. So for example, if one takes the so-called standard map. So the standard map is when one takes I of p. Okay, so clearly it satisfies this condition. Okay, so these are the main ingredients we need to state the main theorem. So as I told you, what we want to consider, we want to study families of twist maps and understand what can we say about the existence of n periodic tori for a given family of a twist map. And so let me mention which kind of families we are considering. So we consider perturbation, so family of twist maps obtained by perturbations by a potential. So sometimes these are also called Magnier perturbation, but I mean, just nothing else than a perturbation by a potential. And so let me explain what I mean. I mean the following. So if we want to perturb a twist map, one of the main problems is that we have to remain in the class of twist maps. And so exactly as you do when you work in Hamiltonian dynamical systems, you don't perturb directly the Hamiltonian vector field, but you perturb the Hamiltonian. So you have a Hamiltonian vector field. So what we do, we perturb the generating function. So my map F, so this is a twist map with the generating function S. And then take G to be a potential. So for the moment, just assume a C2 function. This is a potential. So what we do, we consider the family of generating function obtained by perturbing S by this potential. Okay? And this will define a new family of map. In this case, epsilon can be taken in R because for the specific form. But one can actually could take different perturbation. For example, there could be a dependence on epsilon, or actually it could be more perturbation involving small q and capital Q. I will get back to this. The advantage of this kind of perturbation, except that it's definitely easier, is also that it preserves the fact of being positive or strongly positive, in the sense you see that in the mixed derivatives, the contribution of this will disappear. Okay, so let me state the main theorem. So what is the question? So the question is, suppose I take this family of maps. So, and also observe, I'm not asking anything in principle on the dynamics of the original map. And then I choose one Mn. So this Mn is the analog of a rotation vector. Then what can I say about the existence of Mn in periodic tori in this family of maps? So for how many values of the parameter at most I can expect that such a torus exists? So the question is, for how many epsilon can expect the existence of an Mn periodic Lagrange torus. Okay, so of course the set could be empty because I'm not asking anything about the original map, but also I could start from a map that has one of these periodic torus, and I can ask if it's possible to say something about the presence of such a similar torus in the family. Okay, so this is the content of the first theorem. So suppose F, as before, is a twist map. And then let the S be the generating function. And then G be a potential. Everybody clear? Okay, so assume the following assumption. So the first assumption we assume, and now we have to put some, so that F is strongly positive. Then the second assumption is that actually we assume some regularity on F. F is analytic. And actually, so what we assume for the sake of this presentation is that F admits an extension to CD cross CD. In the sense, one could consider also finite with strip of analyticity, but the presentation and the analysis will be slightly more cumbersome. So let me just focus on the case F admits an extension. CD, and also actually S admits an extension. Okay, and then also G is analytic. So what we can show is that if this is the case, then I look at the set of epsilon such that F epsilon admits Lagrangian Mn periodic torus. Then what we can say about this set, then this set is either R or it consists of isolated points. Actually, one can say something more. So of course, one cannot exclude that it is all R. For example, if I take the potential constant, that would be the trivial perturbation in terms of the map, then of course, if there is a, well, of course, or empty. Yeah. I don't know if you consider the empty made by isolated points, but so I'm saying if G is constant, for example, this set is the all R. But actually, one can say something more. So if in addition, G is not constant. And so we need to ask now an extra condition on. So we want that also the second derivative, not the mixed one. So derivative with Q and Q, small q and capital Q are bounded. Then this set consists of at most finitely many points. Okay, so this is the content of the first theorem. Questions? Yes. Well, here I'm fixed. So first of all, I'm not asking anything on the original map. So the original map might not have any invariant torus. But then I'm looking at the Mn periodic tori. And so what I'm saying is that if I take a potential and then an analytic potential, either I keep this torus for forever, or it will be this only finitely many point. In fact, let me just make a comment on this. Actually, so there are some examples by Suris that actually Misha mentioned. So those examples, they are perturbation of standard twist maps. And so they don't satisfy our hypothesis, but actually, I think one can actually probably fit these examples into this frame with some modification of the proof. But indeed, in that case, the torus persists for all values of the parameters. So with this stuff. Okay, but in those cases, had some singularity, and definitely these derivatives were not bounded. Okay, then let me make some other comment so that, of course, the original motivation was given by billiards, but of course, this does not apply to billiards nor to the geodesic flow, for the simple reason that here we are making a perturbation by potential. And so in billiard dynamics, you don't only have the problem to remain inside the class of twist maps, but remain inside the class of billiard maps. So actually, when you perturb the boundary, that's the analog of perturbing the symplectic, sorry, the generating function in order to remain in the same class, then the perturbation you get is definitely more involved than this. It's not a potential. But nevertheless, I believe that the proof can be adapted also to that case, in the sense this proof is a local proof that uses property of holomorphic function. And so maybe the analog in that case would be that if I have an analytic family of billiards, then either in this family, what is a Mn Lagrangian torus in this case, would be a caustic, it will be more clear from Vadim's talk actually, a caustic made by periodic point. And so either this family always has this caustic, or this caustic appears at most finitely many element of the family. Okay, so I will say if I have time, I will say something about the proof, but as I said, is essentially an analysis. It uses very strongly the fact that these two map are analytics. So what one could wonder now is what happens if I lower the regularity of this map. And so we don't have a clear answer in this case, but we have an answer in the case in which we lower the regularity of the potential. But in this case, we have to start from, so we have to add some dynamical assumption on the map. So far you see, don't have dynamical assumptions. These sets might be empty in most of the cases. Okay, so let me mention about the second part. And so in the second part, we go back to the case of completely integrable maps, and we study rigidity of completely integrable maps. So the idea would be, if I have a map that is completely integrable, then if I perturb the map and I know that some features of this integrability are preserved, for example, I still preserve a foliation, an open set that's foliated by Lagrangian tori, whether I can say something about the perturbation, okay? And this would be the analog of the Birkhoff conjecture for billiards, even though I'm considering a very special case of twist maps. Okay, so let me mention what is this second theorem. I mean, all this theorem are always in collaboration with Marie-Claude and Jessica. So suppose, as before, that F is a twist map, and S is a generating function. Okay, so now let's assume the following hypothesis. So the first hypothesis is that F is completely integrable. So this time I have an assumption on the map. I assume that with the map I start completely integrable, so it has this beautiful foliation by invariant Lagrangian graph. And analytic, of course, as before. Then the second condition is that I take a potential G that's just CQ on the torus. Now I don't ask the potential to be analytic anymore, just the map to be analytic. So for example, keep in mind the example of the standard map. And the third assumption now I want to, so I want to have a condition on how many tori I'm preserving. So what I want to say, so the idea would be, assume that the map remains, the family of maps remain completely integrable for some values of the parameters. What can I say about the map? So, but we don't really need to remain completely integrable. Actually, we need that sufficiently many periodic tori persist. And so the third assumption just clarifies, hopefully, what the meaning of sufficiently many. So sufficiently many, we mean that we have in the rational direction sufficiently many rational vectors that persist. So let me explain it better. So there exists Q1, QD, linearly independent. Rational vector, and there exists the interval, open intervals. So, and consider this such that for every m, I write it here. Okay, so the idea is the following, that there are these rational direction, and in each direction I have some open interval, such that for rational vectors in these intervals, I have the persistence of the Lagrangian tori for many epsilon. So let me take, so such that for every mn coprime, such that m over n belongs to the union of pi qi. So just the union of this interval, this will be q1, q2, qd, the direction, and this would be I1, q1, I2, such that mn belongs, and there exists a family of epsilon converging to 0, such that f epsilon k admits a Mn periodic Lagrangian torus. Okay, so what I'm saying is that if I take rational vectors in this set, then for infinitely many, for a sequence of values of epsilon converging to 0, then the corresponding map has this invariant torus. Then G. Okay, so the remark. Clearly, if I assume that the map remains completely integrable, this condition is satisfied, but actually you need less. It's sufficient to have there exists an open set in the set of frequencies such that this condition here holds for all m over n in A intersected. Okay, sometimes this is called rational integrability. Okay. Questions? No, well, no, here I'm taking this very special kind of perturbation. So in this case, one has to pay attention in the sense, for example, there are perturbations that preserve this family. Take a perturbation that is just a function in capital Q minus small q, then of course it preserves this perturbation. For magnetic, I don't know. Oops, I haven't investigated, but could be interesting. So let me mention that in this direction, there was a previous result by Misha Bialy and Robert McKay, in which they were considering the standard map. And actually showed an interesting result that if I have a map, so a standard map is the one I wrote above, then if I have this map that doesn't have any conjugate point, that somehow is related to the case in which I have a complete foliation by invariant Lagrangian graphs, then the G must be constant. Okay. But of course, the maps we are considering in principle may have plenty of conjugate points, because I'm asking just to have invariant tori in these sets that, first of all, it's not even necessary that the same epsilon k, that are the same epsilon for different rotation vector. But then even if that holds, then these tori don't form any foliation. So there might be conjugate point in the complement of this set, of the closure of this set. Okay, so let me just give, in the time I have, some idea of the proofs of this result. So let me start from the proof of theorem 2, just because it's shorter. Well, it's 2, that's 1. What I'm saying is that I'm saying that theorem 2 is a consequence of theorem 1, which this one is, that's 2. And so this seems bizarre. And there I'm asking G to be C2, and here G is analytic. Of course, if I ask G analytic, it would be a trivial corollary of this. You just need one torus, you don't need the whole family. So actually what one can show is that because of this condition, condition 3 implies that G must be a trigonometric polynomial. And so then once I know that G is a trigonometric polynomial, definitely I can apply theorem 1 and I deduce the, so actually the fact that I have sufficiently many tori is only needed to ensure that G must be analytic. Then it's enough then to have the persistence of one torus to it is G must be constant. And so let me tell you briefly how this goes. This is a classical idea that has been used in many other works. So the idea is the following. So suppose that, so let me write as a lemma. So suppose that F has Mn periodic torus for epsilon that goes to 0. for all for a sequence of epsilon. Well, let's say for epsilon in 0, epsilon 0. But I mean, one can consider the case just for a sequence that goes to 0. It's just slightly more elaborate to write, but it's essentially the same proof. Then the following holds, that for every nu in ZD, different from the 0 vector, then such that if I look at nu m over n is integer, then the Fourier coefficient of G corresponding to nu must be 0. And then the second lemma is that if I look at, under my assumption, if I look at the set of nu in ZD such that nu lambda qi does not belong to Z for every lambda in II and for every qi, for every I1 to D, this set is finite. Okay, one can check this is exactly the complement of that one. So what I'm saying is that because of condition 3, the possible Fourier coefficients that don't vanish are only finite, might be at most finitely many. And so what is the idea of this proof? The idea of this proof, I erase this that we don't need. The idea of this proof is the following. So, so we have a family of invariant Lagrangian graph. Now, what I can do, I can look at the action of orbits on this graph. So I do the following. So I take Q in RD, and I look at the following quantity. So what I do, I take the orbit starting at Q. So let me write it away. This will be just the, well, this is orbit starting at Q. Okay, this depends on Q. Okay, so what is this? This will be just the sum of the action along this orbit. And now, the first observation is that this must be constant in Q. And this follows from the fact that all these orbits are action minimizing. So they will have the same global action minimizer. So they will have in the class with the same rotation number. And so they will have the same value of the action. But then the second observation is that one can do a Taylor expansion for this map. And then what you see is that in epsilon, that's the reason why you need epsilon to accumulate to 0. So this will be as the sum of these. So this will be the action on the unperturbed torus. Plus the first order term in epsilon, that will be the sum, one can show that is the sum of the potential along the orbit, of the orbit Q plus J M over N, plus small epsilon. Of course, if you take a perturbation, it's only a sequence of epsilon accumulating to 0, then one has to pay attention to the regularity of this function. But anyway, it works also in that case. And then you see that since this one is constant in Q, this implies that also this one must be constant in Q. And then if you integrate against e to the minus 2 pi I nu times Q, where nu is in the statement of the lemma, then you get exactly that the Fourier coefficient, the n times the Fourier coefficient must be 0 because you integrate a constant, this times a constant that gives 0. Okay, and so this implies that this must be 0. Okay, okay, so this proves the first theorem. Let me say something about the second theorem. How much time do I have? 2 minutes. Okay, let me say something very briefly about the first theorem, or maybe I do it here. So questions? So let me tell you the strategy of theorem 1 for the proof of theorem 1. So the first strategy show that this set IMN, maybe I shouldn't have called I, but IMN is either R or with empty interior. Then the second point is to show that if it has empty interior, sorry, it has an accumulation point, then it has non-empty interior. And so this would show the first part of the theorem. And the second part of the theorem that I canceled is how we go from the fact that this set is R or consists of isolated points to the fact that it's finite. So essentially we go from the fact that it might be at most locally finite. And so the idea is that if F satisfies the extra condition that I canceled, so remember the condition was that the second derivative are bounded. I repeat, these, for example, are satisfied. These conditions are, for example, if I take a complete integrable map, these conditions are equivalent to be strongly positive because that case, and the finish. Then what one can show, it shows something that is a sort of small generalization of a result by Michel Herman, saying that for sufficiently large values of their parameter, there cannot be any C1 invariant graph. Any invariant C1 Lagrangian graph. For epsilon bigger than some k, this exists. Okay. And so this implies that the set can be at most finite. And let me just make a last remark. So here I'm talking about C1 Lagrangian graph, even though in my hypothesis it was, I said Lib. So, but the observation is that actually these graphs I'm considering, even though I asked from Lipschitz, as smooth as the map, because they can be obtained by the implicit function too. Okay, so I stop. I know, so we use actually the extend analytic. Now the proof, I didn't do it, but it's local, so probably can be written also with a finite strip of analyticity. So what we do is essentially the proof is here. So to show that it cannot be empty interior, in the sense that what you show is that you define some set of parameters for which you have this map, and then you show that this set under some assumption is a complex. If you look at the complex map, is a D+1 dimensional manifold. And then you show that if the set has a connected component, non-trivial, so there's an interval essentially, then, well, you can show that the map corresponding to looking at the image of the map minus Q minus, I cannot really explain, but anyway, some map vanishes. And then using the fact that this map is holomorphic, it means that it vanishes in the all connected component of this. And so actually that you can extend the set of periodic tori. And then you have to also show that these tori are also Lagrangian, or not just, but the idea is the same. That is the vanishing of the holomorphic map on some submanifold of real dimension D+1 will imply that it vanishes on the all connected component. Well, let's say the proof is written in this case, but actually I am pretty sure that the proof can be done also when you have a finite strip. In the sense, the proof is essentially local. It doesn't really look at what happens. I mean, you have to put probably some condition, I mean, to pay attention on where these tori are located, I guess, but that shouldn't be a big problem for this part of the proof. I mean, for this theorem one.
One of the results was that the convergent condition is G factor that enters the gradient factor constant. What would that for this map?
For a twist map, so that the map doesn't change. So I'm saying that the perturbation I'm doing is trivial. So I'm saying is that if I have a map and I perturb the map so that it remains integrable, then I'm not really perturbing the map. Well, definitely the result by Misha I was mentioning has a relation with the Hopf conjecture. So in that case, so you say they are not conjugate points. So actually, if you don't have conjugate points, then the map is C0 integrable, right? And so what so I have a foliation by this tori, and so I have periodic tori for all M on over N. So let's see. Yes, the one that without conjugate points implies C0. Yeah. There is a result by Marie-Claude Arcostanzo. No, Arcostanzo? Okay. Flows, okay. Yes. No, but the potential it was using for perturbing. So actually, first of all, there was also dependence on epsilon in the potential, but then it doesn't satisfy really, well, all these assumptions. But anyway, so what you showed is that for all values of the parameter, it remains integrable. That would be exactly this set being R in our case, but in that case, the set of parameters for which the potential still remains, because then. Yes, but I think if you perturb the flow, then you're not really perturbing by potential, no? Okay. Yeah, probably for flows it's slightly different. I mean, I'm talking about the maps. Maybe for flows it might be that you need more condition too. Yeah. Yes. Well, I mean, I guess it's kind of yeah. So what he's saying is that so if you have a C1 Lagrangian graph without any condition on the dynamics for a twist map, then these are Lipschitz by Birkhoff theorem, and then actually you can have a bound for the Lipschitz constant. And so what you can show is that if this, so the on the Lipschitz constant depends on this. Show is that if these are at some point, you get some epsilon times these more or less, they will grow too much, and so you cannot Lagrangian graph cannot be really Lipschitz anymore, satisfying that bound. But, okay. Thank you very much.